started.
Okay. Maybe I explain a little bit what's happening in the source code of the library. So the library gets compiled using using this makefile that we have, and the makefile requires to be run in, I don't know, bash shell or a Z shell if you have on your computer. If you have any sort of emulator, it can compile all the codes into a single file. If I run make, it will generate the source code, as you can see, in that directory. And if you go through the source, there is a header file that doesn't change much, and there is a main file that actually has all the JavaScript files, and there is a subfolder that is called shaders that has all the shaders that are necessary for all the plotting algorithms that we have in the library. They didn't want you to go through the entire library. Also, if you have gvim or this project.sh, if you look at it, it's just simple file that basically simple shell file that basically opens all the important files that exist in the library. So there is a main.js, which implements all the JavaScript, the header for that JavaScript, and there is a tail section that adds after that. And we have a bunch of shaders in the form of fragment shaders and vertex shaders that I use. The default vertex shader is actually somewhere down there as well. So it opens all of them. So you can change this shell script to the editor of your choice to open all the source files if you want. Similarly, I don't know if you have noticed, I have the same sort of project file when I have this multi-file system for the projects that we are dealing with. So if you run that project file, and if I make everything a little bit larger, and if you look for the term volume raycaster, you see that actually the definition of the class is somewhere here. These comments might have changed, so there might be additional options rather than the ones that you just see here. There are several ones, but you see the options are processed at the top of the file. These are all the options that get imported. And then there is a copy that happens. There is a coordinate section that actually calculates the coordinates. I will explain all of these ones, but there is at least this solver that runs only once when this program is executed or this class is defined. There is a solver that deals with the lighting. So that solver is this guy here, which uses the default shader and some other fragment shader. It has all these uniforms, and in the end it creates a lighting texture that basically has all the information that is required for lighting. And then, since we want to plot everything in 3D space, we need a cubic geometry. And if you notice, we have a wireframe around it as well when we are plotting. So there is a wireframe geometry as well. So far I have brought all of these guys in. And then there are additional parts that need to happen, like when you need to have a model matrix that I will explain. And there is a view matrix. that actually does this transformation when you are changing the cube. This viewpoint needs to be updated. So that is done by updating this matrix basically. And there is this controller that basically manipulates this view matrix that is updated using this orbital camera, which basically has a bunch of features. You can rotate it, you can zoom through it, zoom out from it, and all of those ones. So you can use these ones to expose them. And then there is a final projection matrix that uses a perspective point of view that is defined using a matrix is created, then it's defined as identity, and then the identity is changed with this information that we have here. We need to recreate all of these ones. So if I want to explain what is happening in the background, there are basically two important steps involved. And one step is that in the end we want to show something on the screen, and we want to be able to color what's happening inside a cube. So we have a cube that we want to show. And this cube is going to be in the end projected on a screen. So this, let's say this this purple section is the screen. The first step is to actually visualize these three parts that I am highlighting. There are three surfaces that if I color them, these will be these surfaces in the background. These surfaces that we have here, these three surfaces that are in the back. If I figure out what is the coordinate that is here, 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 all on the screen, I can project all of these coordinates to the screen. What will happen is that on this screen that we had from copy everything. I will know in one texture I can store this information about these coordinates, and the size of the texture can be exactly the size of this screen that we want to show. I will have the the back coordinates. So this can be called the back coordinates. So instead of coloring on the screen, the color would represent the color represents the coordinates on the back of the cube. And I can do the same thing to just color the coordinates that are the front of the cube. So I could have another version that is the front of the cube. I can have this, but instead of this part, I can remove the back parts and just color the front parts that are visible to us. This is the important part, maybe. I can do the same thing with the front. In the second step, I know I can determine what is the coordinate on the front. So this is the coordinates on the front. Now what I want to do is actually I want to color the front. I want to color the front face such that I am calculating the volumetric data, or I'm creating a representation of the volumetric data. And in order to do that, all I have to do once I know the point that is on the front, I can compare it with the same point that is in the back. So I can find the corresponding version, for example, here. This can be the corresponding version in the back, sorry. So I can find the corresponding version in the back. And using those two coordinates, I can actually create, so if I assume that if I look from a different angle, I can say this is the front point, and on the same point on the screen, I can have the coordinate of the back face for the same location. So my eye is looking exactly along this direction. When we are looking at the screen, we are seeing from the front, and we are looking to the back. And at this point, when I'm looking, I already know what is the back and where is the front. So from here, I can generate basically a vector that I can march. And let's say there is, I don't know, a flow field or whatever whatever voltage field that you want to visualize is the field that you want to visualize. I can start marching from here by little vectors. I can move forward, and I can look and see what is the value of my 3D field at that particular point along this vector that I'm moving. And as I'm moving, let's say this is where the voltage starts to become visible. So you have to start at thresholding value. You can't, if you visualize the entire domain, then you would just see the surface, right? Whatever is happening on the surface. Once you want to visualize, for example, maybe you want a certain level set. Maybe this is the level set that you want to calculate. Level set of V, let's say, equals to 0.5. Anything below 0.5 you disregard, and then when you start looking at here and you see that the voltage is higher, you can start adding the colors to this as you're marching along. And by applying a certain level of transparency by using what is called alpha correction, you can say I calculated the color here to be maybe C, C, C local, or C whatever color that you want to calculate. And you have a summation color that is the end color result that you want to calculate. You start adding the color that you see over there times the alpha correction, which is usually a number that is smaller than 1. So if the number is just 1, you would just calculate the final color. But if you, let's say you set it to 0.1, you you only get 10% of the value of that color. And you keep marching, and then you can have, at each point, you can have this uh, thing called accumulated alpha, that each time that you can read, you add that alpha to that accumulated alpha. So what happens, this is the pseudocode. So you have a for loop along the array, or along this array that you wanted to have, small steps. For all steps, you check if v is above the certain threshold. If v was above the certain threshold, you add the color and you accumulate some alpha. Once once alpha reaches 1, basically this whatever you calculated is fully opaque. You can't see anything beyond that once you reach full opacity. So the place that this loop breaks is that if your accumulated alpha is greater than 1, or if you have reached the backface. If you have such condition, you just break this loop. If you encounter such condition, you break the loop. Otherwise, you keep going through this. So you keep adding the colors. Here, you don't add anything. In these sections, you don't add anything. Once you reach here, you start adding colors as you are progressing through until either everything is fully opaque and you loop out, or things are not fully opaque and you go through and you reach the back face, and then you can stop. So that's basically the logic that we have. So for each of these points, array will be defined that goes from the front plate to the front face to the back face, which is here exactly. So the front is here, back is there, and the line that you see is actually going through there. So it's a vector that is going through there. And we keep doing that. Okay. So these are the steps that we have. And so far, what I have converted from the two codes is I have brought the coordinate texture, and the coordinate texture is nothing but just looking at the 2D data structure that we talked about. We said that we have a matrix of z slices. Matrix of z slices. This was our data structure. We had mx divisions in here and my divisions in there. And then we had subdivisions in those regions that each one of them was representing something. So this was our actual data structure. Data structure that we had. What this
Abuja, are you drawing something?
Yes, sorry. So we had this data structure that was that had um, some Z slices in it, and it was going from the top to the bottom, if I remember correctly, what we were talking about. It was going from the top to the bottom, so this was coordinate Z equal to 0, and Z kept increasing in that direction, and then in that direction, and so on and so forth. And X and Y's, X was in that direction, Y was in that direction. And what this coordinate texture is representing is actually representing what would be the coordinate of each pixel in the 2D structure, in the 2D data structure that we have in the 3D space. So if you remember in the previous sessions, we had a cube like so that had our data, and we had some Z slices like so. So here we say, what is this corresponding to, basically? So we have the coordinates for each of these guys stored as the value of the pixel. So that's what that solver is doing. The solver is using something called VRC light shader, and VRC coordinate shader, or CRD shader. If you look at it, it's very simple. It's basically looking at the pixel coordinate on that 2D structure. Looking at the pixel coordinate on the 2D structure and deciding what should be the coordinate in X, Y, and Z for that point, and returns that as the color value for that texture. And this can be useful if you want to have the coordinate at any point, instead of doing these calculations each time for the current value of the pixel, we can just access the texture and see what would be the coordinate of that point in the 3D. So that's what this guy is doing, and that is why when we calculate that, we just have to run the coordinate renderer just once. And then for lighting purposes, we have two sources of light, something that I call the floodlights and then point lights. And for lighting, so let me explain what are the floodlights and what are the point lights. So if I had a floodlight, it would be just a directional light that is uniform and is lighting in that certain direction. And if I had a point light, it would be a point that is sending out rays of light like so in various different directions. So what happens is that for each of these guys, I wasn't. So the floodlights were uniform lights that you just determine the direction, and they are uniformly lighting everywhere in a space. Where point lights, you put them in a certain place and they start shining lights in various different directions. So it's just a point source of light, as the name implies. And in order to calculate the lighting value, you could imagine that if I had a floodlight, I had to start from some corner and then go in the direction of the light into the 3D geometry and see whether I can hit a certain surface or not. And in order to determine whether light reaches a certain region, is that as I am moving in that direction, if I reach a certain area that I illuminated, I look at that point, and based on the opacity that I have, I can say how much light remains to go forward. And then the moment that the amount of light that I have inside goes zero, the effect of that light would be just that region that it lighted, for example, that ray of light. Similarly, I have to do the same thing for these point lights. So the point lights are a little bit easier to handle. You just have to look at each coordinate and just march through it back to the point light to see whether something was in front of you or not, to be able to light that region or not. Right. So if you look at the light shader, basically these intensity calculators are in charge of, you pass a point light to it or you pass a floodlight to the floodlight intensity function, and in the end it determines what should be the value of lighting for that particular point on your texture. And if you notice, we pass the coordinate texture for each point, and we determine for the coordinate texture what should be the lighting value on that point. So it works with the coordinate texture, this function here. What it needs is mx, my, the target value that you would require, as well as the number of directional floodlights that you have and the number of point lights that you have. And these are arrays of vector-3 types with maximum number of 100 floodlights and 100 point lights that you can define, but you can change this maximum number. So here I've passed to this function, to this lighting function, 5 floodlights, one coming from the coordinate 1, 1, and 1, the other one from 0 and 0 and 1, and these ones, so these are the coordinates as you're sending them. So I think Max was asking once, how can you pass different vectors of different types? So here is an example of sending a vector of an array of vector-3 types to the texture. The values of the vector-3s are sent one by one in a single array to the GPU. So this length that you are sending should be smaller than the maximum length that you have over there. Match that.
Okay, you intercepted my question. Thank you.
Yeah, you're welcome. If you don't send anything, it will be assumed that they are 0. So for example, for the point lights, I haven't sent anything, so it assumes that everything inside is 0. And the number of point lights I have explicitly sent to be 0. Okay. Next thing is to define the cube geometry. The cube geometry is defined using this, and there is the frame geometry that has some bunch of line segments basically that you see that I've defined. Each one of these pairs is basically one of those line segments. I can just check it out. This corresponds to that. The next step is to, okay, so this is part of the library. If I want to expose it here, I just copy here thing that we had. I want to show how we can do this part. bunch of stuff that we will require. So this should be changing to some sort of var. This mat4 changes to Abubu, probably. Model matrix. All of these require the Abubu part to be added. You don't need that. Need that. Don't need that. Okay. So we start with an identity matrix, then we rotate it by negative 90 degrees along the x-axis. So let me explain now what this model view matrix is. Is that when you have any sort of geometry, you create, let's say, this geometry. This geometry usually has its own x and y and z coordinate system, and you can move this around into the physical world. Let's say if I wanted to show this cell phone and represent or build this cell phone, when I'm building this, probably my coordinate system is somewhere around the corner, and I say that the length is so many points and the height is a certain point and the width is another value. But later on, when I want to represent this into the graphics system, I have to place this model inside the room, and the matrix system that actually is in charge of changing the coordinate from the phone into the room coordinate system is what is called the model view. So let's say this is our geometry, and then this was our clip space that we talked about in early stages. Or maybe I just call it room for the moment. So, and let's say this had some coordinate system. The room had some coordinate system called x prime, y prime, and z prime. So the way that we go from x, y, z to x prime, y prime, z prime is through this matrix conversion from the model view matrix multiplied by the object's coordinates, object coordinates. I should be able to get the coordinate in the model coordinate in model world. Some people say that the model view matrix takes the coordinate from the model world into the real world coordinate system. So from the model into the real world, if you want to convert it, you multiply the coordinates of the model by the model view matrix to go into the real world coordinate system. Or so this site could be called also real world coordinate. So once we place something into the real world, then we can use a camera and take a picture of the room. And basically, in order to do that, we have to decide what part of this room is the clip space. So this could be something that is completely in a different orientation. It could be something like so. Could be another coordinate system. Maybe you like to hold your camera like so. I don't know. Whatever makes you happy. So this is your projected world. Projected image. So your camera basically wants to take a picture of the real world. It does some sort of transformation on the real world coordinate system. So the next step is the projection matrix times the model view matrix, or maybe you call it the real world coordinate. And what you get is the projected coordinate. Okay. These are the several steps that are involved to project something on the screen. So first you have to change the model coordinate into the real world coordinate, and from the real world coordinate into the projected coordinate, and that projected coordinate can be displayed on the screen. Okay. This gets displayed on the screen. So here again, what we did is this model view coordinate system, which we rotated everything by 90 degrees. Okay, and then we moved everything. Okay, so one thing that I want to tell you, it's the order of applying these transformations is that you have to remember this, that as you're applying different transformations, for example, if I had an object that was here and I want to translate it to this point here, and let's work with something that is a little bit easier to deal with. I translate it to here like so. This is my first step. And then I want to rotate this by, let's say, 90 degrees or something like that. So it becomes this triangle like so. When I'm multiplying everything, so we have the model coordinate. Let's call it, let's see, MC maybe, lowercase mc. It's a vector. We do a translation first, and then we have a rotation here. Translation T, and then rotation R. So what happens is that the MC coordinate needs to be translated, and when it's translated, it needs to be rotated, right? So the rotation matrix is applied. So if I want to have the entire transformation as just one matrix that gets multiplied, you can notice that I have to have, if I start with identity on the left-hand side, I have to multiply it by rotation first and then by translation. Okay, so does that make sense? We start from the model coordinate, we do a translation to it, so that's the translation part that happens, and then we rotate it. If we rotate it next, then when I want to create just a single matrix for the entire transformation that happened here, if I wanted to represent this entire transformation, then I start with the identity, then I rotate, and then I translate. So it's the other way around that I have to put these matrices in. So that's why you see here the first thing that I wanted to do. If you remember our clip space, the coordinate was running from -1 and -1 and -1 here, and it was running to 1 and 1 and 1 in that coordinate. So if I had a matrix, if I had a cube that was a unit cube with its coordinate being 0 and 0 and 0 in this corner, and 1 and 1 and 1 in the other corner, what I have to do is I have to shift this in the center so I can easily start rotating it. If I want to put that, if I want to be able to easily rotate this object so that it doesn't go out of the screen, I have to place it in the center of this cube so that I can rotate it around the center coordinate system. Otherwise, it will move all the way around. Okay, so if it's placed there, if I rotate it, it will go there. So we don't want to do that. We want it to be at the center so we can rotate it. So the first thing that we need to do is we have to translate it into the center, and then we have, if we want to place it a little bit rotated, remember we are looking from this direction. When we want to project it later on, we are looking from this direction. So if we look at it just like that, we will just see this portion in the front. We want to look at the sides of the cube a little bit. As you can see, when we start, we are looking like so, instead of looking something like this. And there is another point that we want to actually do this sorts of perspective vision that we are going to create using our projection matrix. So what happens is that we do the translation as we are putting everything together. Last, we start with an identity matrix, we do the rotation, and then we multiply it, then we translate it, basically. So the identity is multiplied by the rotation matrix, and then the rotation matrix is multiplied by the translation matrix. And then the view matrix is created. So I can put a view there. And this view matrix what we want to do is we want to start, so we have to look at it from the back, whatever happened at the last part. Just looking at a certain point, and the lookat function, if you look at the so looks at the view matrix, the lookat point, I think one of them is the first one is the starting point. The next one is the point, the coordinate of the point that we want to look at, and then the next one is the direction of your point of view. So we are looking in the y direction, which goes into the screen, I think. This thing is just for debugging, I think. And then we have this is the controller part. Changes the view matrix, basically. So it receives the view matrix, and we have to have canvas 1 here that you're using for plotting this previous X and Y. I don't know what they are. I have to look at the documentation for that. That basically uses a camera control. And the camera is a perspective camera. These are all for viewing purposes. So I can remove all of these sections. You have to remember to define field of vision, display width, and display height. And the far field. So, and if we look at the, okay, so the camera works like this, that it has, if you have a perspective camera that is looking, so this is the projection matrix that is going to work. This perspective matrix that you see here creates a perspective camera for you. And the way the perspective camera works is that if this is your eye, it says that what is this angle that you want to create. This is usually called FOV, or field of vision. So anything outside that is ignored, basically. What is the distance from you? So this is the near field. And then what is the distance of the far field? And then, okay, so we can actually read the documentation for this. So FOV is the field of view in radians. The next number is the aspect ratio of the width to the height. So the aspect ratio of this section that you're looking at, so that display divided by height is that aspect ratio of W over H. That's why we calculated that. And the near bound of the frustum that you're looking at, and then far bound of the frustum. So looking at the default values for this is 0.1 radians for 0.1, pi over 10 basically here. Near field is, I think, let me see, the default for this is near field is 0.01. It's almost close to 0, and then the far field is at 100. So we can put these values here. One and then 100. And then this one is near field. so then comes those two steps that I explained, pass 1 and pass 2. So the pass 1 would generate the backface coordinates. So we need to create the backface coordinate to be new type of texture. And our size of these guys were 512. This aspect ratio is also 1. So remember, now this texture is the size of the screen size. And then from the library, you can create the pass 1. So here is the case that the vertex shader and the fragment shader are not the default versions. So the first step of the vertex shader. And the fragment shader also has a custom shader. RC2 fragment shader. So here we are passing the matrices that we generate, view matrix and the projection matrix that we have. And the geometry is the cube geometry. So there is, you have to use a feature called call facing, and call facing means that which one of the faces you want to be called, which if a surface is pointing, the options that you can have is front and back. Here we are saying that if the front of the surface is looking at us, is facing us, we want to remove that surface. So this section in here where I was explaining that I was going from this picture here, and I wanted to ignore whatever surfaces was in front of me, and I wanted to just look at the back surfaces. What I was doing is I was calling the surfaces that was in front of me. So I'm just going to remove those surfaces from the view. So that call facing is that part that I talked about. So I'm facing the front. I have to do also a depth test to see what is in front, what object is in front of the other object. So this might become important. And then when I calculate everything, I write the backface coordinate as the target. So now let's look at the vertex shaders of it and the fragment shaders of it to see how it does this sort of stuff. I think when I was going through whatever we were calculating, I said we always use a default vertex shader. This is one of those examples that I don't use the default vertex shader. I bring in the position, and one of the things that I create is this world space coordinate, because I want to know what is the coordinate of, I may want to know what is the coordinate of each pixel in the world. And then I want to have the view matrix, the model matrix, and the projection matrix. So what happens is that whatever I return for the world space coordinate is the position of the actual fragment in the model world. in that coordinate space that was going from 0 to 1 because talking about when we were talking about this guy here, everything was going from 0 to 1, right, for this guy. And this is the guy that actually represents our computational domain. So we want to know exactly what are the coordinates in this world. So our world is basically what I return as the world coordinate is basically that guy, coordinate in that place. So again, in 2D, you notice that we were doing interpolation based on the position of the points. We were generating a vec2 type, and that was pixel position or CC. Here we have world space coordinates that we are returning. And then our projection happens as we start with the position vector, and then we multiply it by the model matrix, the first thing that happened, so that now this is our position of the object in the room that we want to take a picture of it. Then we have our view matrix. So if we change our head, we're changing our viewpoint. And the last thing that we have is the camera in our hand, that when we changed our place in the room, we bring the camera in front of our face and we take a picture. So this is the last part that we are doing, this projection matrix that is multiplied to that. Okay, does that make sense? So we start with the position of the points, we multiply by the model matrix, so we take it to the world, we place it there, and then once we placed it there, we decide at what angle we are looking at it. Once we decided at what angle we are looking at it, then we take our camera and we take a picture. So that's projection matrix that is multiplied last. And that will be the fragment position on the in the clip space, basically. So this places the object in the appropriate location in the clip space. Okay. And then when we go to our fragment shader for the first step, all we have to do is we have to return the world space coordinates for the point that we calculated. So we have a coordinate, we calculate all of that stuff so that we know where we want to draw it, and then when we decide where we want to draw it, for the color of it, we return the coordinates of each of these fragments. So basically, what it returns is the value of the pixel, the coordinate of that point on the back plate that is over, basically for the color. So that's what's happening over there. So that's our pass 1 that happens. And then we have pass 2 that is way more complicated than this. So I have to remember to add the Abubu part to this. Bring the pass 2. There are a bunch of stuff. There's a lot of them we need to remove because they have nothing to do with what we are going to do right now. Of the additional stuff. This would be, we need to source the vertex shader for the second pass. Is everybody still with me? Or are you super
I'm here.
confused? Okay, you're here. That's good. So these are the parts that, okay, so present, this is, I need to remove these sections. There's nothing. Yes. Moving these keywords because it shouldn't be there for our purposes right now. Okay, no, you're done with that. Okay, so again, what we would require to do, let me go to the, we can go to the definition of the solver, but for the vertex shader, the vertex shader of the second pass is also very similar to what we had before, except in this section, we pass two things. One is the world space coordinates, and then the projected coordinate. I don't remember why I used the project coordinate, but I've kept it. So I think I was calculating, we will look at it, I think we were calculating two things in the end as the targets. Was it being drawn in this screen? Uniforms. Those two are the targets. Geometry. Okay. I think we need to draw this one to the canvas, if I remember correctly. This is the part that I have to figure out what I have implemented a couple of years ago. These are all for filament calculation. Pass one, pass two. Canvas. Yep, so what we need to have is we need to write canvas here and canvas one. We want to draw the results on canvas one. And the fragment shader is the part that actually all of the calculations are here. Let me see. Okay, so I have everything. So basically, when we start, we have a see. So that's the so there are a bunch of stuff that we won't use, like the X level, Y level, Z level. We don't use that. filament color, we don't use. Filament, we don't need. Draw filament, show X cut and Y cut, we don't need. Use face field, we don't need. VR raycasting, we don't need that. Compression map, we don't need. Base textures, we don't need. We have a color map, steps, alpha correction, MX, light shift, structural alpha, we don't need. And then we calculate the fragment color. These are the stuff that are actually necessary. All right. So what you will have is also this function. This basically the previous texture function that we had in other places, it didn't do any mixings of the colors. Here, basically what it does is it has to do multiple interpolations in 3D space because each of the points along the ray may not end up exactly at the center of a pixel. And if you want to, in the center of a texel, and what you want to do is you want to have some sort of an interpolation in the 3D space so that you calculate an appropriate color. So maybe that could be the source of error that you will need. This is the basically where everything starts happening. This is we start getting the projected coordinate of the texture on the screen. So we need to know what is the coordinate on the screen. So that's the projected coordinate on the screen. And then we get the position on the back of the face of the cube by reading whatever is the back face coordinate texture at the texture's center. So exactly on the 2D texture, we look at it and we look at what is the back coordinate. We look at the front coordinate, and the front coordinate will be basically the world space coordinate that we have. So maybe, I don't know, maybe that's the source of the error. You have to look carefully. And then the ray that we want to cast along is we subtract the back from the front. Basically, that would generate the ray that goes from our eye to the back coordinate. The length of the ray we can determine. The marching length is the number of steps that you want to take from the front point to the back point. So the more number of steps that you have, the smoother surface that you would get. And then this is the array that you use for marching. Basically, you calculate the length that you start from a certain point, how much you want to go further to the next point that you calculate, and you continuously keep adding to that point. So you normalize the array and then you multiply it by the march length, how much length you want to go forward. You start the current coordinate that starts from the front. Your accumulated color would start from 0. Accumulated alpha should be also 0, and accumulated length you start at 0. Then you initialize or you define some sampled values that you start sampling along the textures. And what you start to do is, this is the marching loop that happens that I talked about, that you start sampling the target at the current coordinate that you have, and based on the channel multiplier, which color channel you wanted to visualize. Basically, you do a dot product of the sample target and the channel multiplier. So what happens if you wanted the red channel, you pass for this 1 and 0, 0, 0, I think. And You can scale this value. For our color map, we use something from 0 to 1. So you scale the sampled value to a value that is between 0 and 1 based on the minimum value and maximum values that you have defined. You also sample the lighting that existed at that point. If the sample value is greater than the threshold, then the sample color is calculated based on the color map that we passed through and the value that we scaled right now. We calculate the sampled color. Our sampled alpha would be the alpha correction, and the sampled and we rescale the sample color by multiplying it by the sampled light. So if something is completely dark, there is no light coming to it, it will just be black. And if something is some light reaches to it, it will have the color that it has. Otherwise, if the threshold was not above that value that we were looking for, we set the sampled alpha to 0. I don't know. I'm looking for the sources of the bug as well as I'm reading and explaining what's happening. And then the sampled alpha becomes the scaled value that we had over there times the alpha correction. I don't know why I did that. And the accumulated color becomes the previous value that we had. Let me see. I don't know what happens if you remove this line here. I know that they changed the visualization effect. I don't remember why we put this thing here. We can remove it later on. And the accumulated alpha becomes the sampled alpha added to the previous value. And the alpha channel of the accumulated color would be the accumulated alpha. And the current coordinate will be marched forward, and accumulated length would be the march length added to the previous length. So at any point, if the accumulated alpha is greater than 1 or the accumulated length is more than the ray length, we set the accumulated alpha to 1, and then we break this loop. And what we return is the accumulated color. That's what's happening. So we can start removing the stuff that wasn't necessary from this part. So we have the model matrix, backface coordinate texture we added. We don't have any face texture. You're not using face field. You can remove that. The target that we want to plot in this example is the F color texture that we had. We don't have that. Light texture we calculated. Filament we don't have. Draw filament. No X Y level. These are all regarding visualizing the filaments. Remove all of that. And this main value was, I think, 0.5, max value 1.1, threshold maybe 0.5. And the channel multiplier was, we want to visualize the red channel, so we pass that guy. Alpha correction was 0.15, and number of steps, say 120 steps. MX, environment MX, environment MY, light shift, and 0, and no structural alpha. Cube geometry, canvas 1. Okay. The only thing that we don't have is this colored value. Can make this one a little bit of life easier here, and generate a color map on the fly. Gate value. A lot of changes that I made. Bump map and texture. Oh, this was for, you don't need this function at all either. Varying with the same name but different type. This is V2. Out vec3, world coordinate, out vec4. And color map is not defined. Problem solved. Feel unhappy about something. Shader are not declared in vertex shader projected coordinates. declared. Okay, now we have a problem here in compilation. Anybody has any idea what I messed up? Okay, welcome to my world. Very sad about something. Alright, with the same name, different type. Not true though. Fragment shader. Complaining about projected coordinates. App section. The RC2V shader. What about this part? Not even there anymore. Oh, there was a problem there. Should have fixed it now. Okay, everything compiles now. I'm going to remove the plotting that we had before. Neil, are you still here?
Yeah, I'm still around.
Okay. So the next part, when we are basically calculating everything, we have to have a pass one. We have to render it, and it calculates the location of the backplates, and then pass two is supposed to I don't know whether it will work or not. It's supposed to calculate whatever is happening. So let me see if you see anything on the screen. Oh, something.
Oh,
Okay. So I plotted something. Remember that there was something that I had to plot this guy twice. I don't know why. It was like that. Plot it twice to reappear. Okay. Okay. In order to take the, right now, if I change anything with the projection, it will not update. So what it will need to do is I need to look at my source code. Again, I think I closed it at some point. I got frustrated. The volume raycaster, I think this is too small for everybody to see. But when we are doing the rendering part, the rendering part is actually doing a lot of stuff for doing the calculations. Has a bunch of stuff for clicking and getting the click values. Drawing a color bar, setting maximums and minimums, a number of steps that you want to use. Render function. Okay, render. So we need to update the controller and update the view matrix each time that we are updating. We want to draw these stuff to these screens. So let me see. So where we were calculating these stuff, where we wanted to display everything, we have to update our controller. Pass 1 needs to be updated with the new view matrix. This S, what I don't remember what this. SSD scale. I think there's a 0.5. I don't know. Did I get the scale? Sorry. Put this. This. Yeah, this is 1, so 1 there. Okay, now we can rotate it a little bit. Okay. Now that you know the details, that is a lot. You can try to figure out what's going on these top and bottom portions. So what I've tried to do right now is to isolate everything. I've stripped down the code to just where it is doing this, all of these stuff. So I stripped it down to all these sections that you notice.
Was there anything wrong with what we just were looking at?
Sorry?
Was there anything wrong with what we were just looking at? I mean, it when you were rotating around, it looked.
So you notice that this section here.
Yeah, right.
it shouldn't be any activation, but when you're looking from the top,
Right.
something is happening, which I don't know what it is and what is causing it.
Yeah,
It's
that's still
something to do with lighting, or I don't know. I don't know at all what is going on in those sections. I don't know.
I kind of have a couple general questions.
Yes.
Let's see. So,
Make this and add all of the changes so that you can do a push for all of these things. Yep, go ahead.
okay. So I guess the when you're doing the accumulation of colors, using starting along array, which goes from the like from the observer's point of view, backwards toward through the cube. I would have thought that process would have to be done last, right? I mean, you have to do all your transformations first, and then at the very end, then that's when when everything is in place, then you can look at the single ray and figure out
That's
like
exactly what's happening, exactly as you said. So the first step is to calculate where the backplate is. So you look at it where the backplate is, and the next step that you do, that is you are doing the marching, it is afterwards that you get the coordinate of you do two things at the same time. Is that you can do it actually in 3 steps. You can calculate the back plate, you can calculate the front plate, and then you can do the marching. But when you calculate the front, you can already start doing the marching in the same shader, so you don't have to launch the same thing twice. Okay. So this is also something that is really mysterious to me. This is the only instance that I have to run something twice. I think maybe there is a clear here that I'm doing that I should turn off. I think clear off false. I think it should get rid of that problem. Let's see. One bug down. Let me see. Yeah, then it messes up with some other stuff. You see, it creates other problems. So this last step
do
is
here and there someplace.
Yeah. Some clear must happen at some place that I'm not doing it. Maybe at the beginning of the first. So maybe I should do a clear before on pass 1. That's why it's causing this problem. Clear. Move here. Here. Holster. I know that something was causing all of these problems. No, I don't know. Something is weird about this.
Yep.
3D1 is just like really complex in several areas. The only way that it plots it semi-correctly.
Yep.
So this second pass is actually the marching algorithm that is actually marching along the point of view. And if you notice, that is the last part in the in our loops. Library. Yeah, so this is the last step. You march the solution several times, and then you update your controller if you have been pushing and changing stuff around. And then you calculate the new view matrix based on the old one that you had. If there needs to be a scaling, you do some sort of rescaling it. Plot this stuff. I'm not sure that you need to do this part. Probably turn that one off. Fine. Yeah. So in the library, there is an extra step that draws the frame around this
Right.
guy, and there is another extra step that generates the color maps that you want to calculate. But if you manage to fix what is wrong in the shaders, we can actually apply to the part that is the corresponding part in the library.
Okay.
You can have a look at it, the lighting algorithms for those of you who are interested in improving the, so you see there is some sort of other bug in this region that I don't know whether it is due to the lighting or what is causing that. If we remove the light effects completely, so there are different things that you can try. So in all these stuff that are happening that are mostly problematic must be somewhere that are happening here. So for example, if I want to take out the light effect, it's just this part that I have to just ignore. Probably that will take care of the lighting issues. It will be just other issues. I don't know if I can see the effect of the light. Search for the word light.
So if I wanted to if I were to try to construct this lighting, with this is just the opacity thing. I would have thought that I would work from the backwards, like from the distant point back towards the observer. You take like the first pixel that that you want to display, multiply that one by alpha, then take that whole quantity, multiply it by 1 minus alpha, then add the next color, if that's to the front, multiply that one by alpha, then take the whole thing, multiply it by 1 minus alpha, and go all the way forwards like that. So your algorithm runs the other way, right? Your algorithm runs from the observer backwards.
Both of them are possible to do. The point is that when you are moving from the back towards the observer, then you can reach a maximum opacity at a certain point that is not closest to the observer. So that's not the correct
You're
thing.
always multiplying by 1 minus alpha, though, so it seems like you should never ever you should never overflow it. I mean, it should always be, that's always going to be, I mean, at every stage, it's always alpha times the color plus 1 minus alpha times whatever's behind it. So you should, like so the sum of that should never exceed, like the range of colors that you have, because it's always alpha times something between, let's say the color values run between 0 and 1, then you're always multiplying alpha times something which is between 0 and 1 plus 1 minus alpha times something which is between 0 and 1. So it's always going to be between 0 and 1. And to me, that's the way that way opacity actually works. That it's opacity times the color plus 1 minus alpha times what's coming in from behind.
So you can try that and see what happens.
Yeah. So I guess there are a couple things that confuse me. Like I just mentioned again that when you're doing translation and rotation, and it's from one coordinate system to another. Okay, first of all, to me, translation is not a multiplication by a matrix that you're adding. It's a translation. You're translating all the coordinates, so it's actually not. It doesn't correspond to multiplying by a matrix. Rather, it corresponds to taking the value and adding a constant vector to it. So that's not a linear it's not a linear operation, because like the 0, 0, 0.
So that's when the fourth coordinate comes in. So if you notice that for the coordinates, we had x, y, z, and then there was a fourth coordinate that actually starts playing around in the translation. So when you are multiplying, is actually that fourth number is added to something there in the matrices. So with the matrix transformation, a little bit of the fourth one, which is always 1, is added to the previous ones. So everything in the end becomes like a matrix multiplication.
Okay.
That fourth coordinate is where it becomes important right now.
Okay. Yeah, I guess, yeah, I know that there's this use of a four-dimensional system in 3D that that people will use. Yeah, okay. So yeah, I'm not familiar with that transformation, but I'll go. Is there a name for that transformation where you're operating in 4D to do 3D type of operations to the or coordinate transformations?
So, sorry, I didn't understand the question.
I know there's this trick where you can operate in 4 dimensions to do translations and rotations, translational and rotational types of coordinate transformations in 3D.
Mm-hmm.
I think that's what you're talking about.
Yeah, that's what I'm talking about. So the fourth coordinate in computer graphic is used so that all the transformations can be done as matrix multiplications, and then you can do in a sequence of matrix multiplications.
Okay.
And the other part is that I really don't want to generate the matrices myself because that's part that should be really easily done, and that matrix, I think it's math.js, is part of a separate what is it? It's the part that we looked at it like it's this is GL matrix is one of those libraries that allows you to do a lot of these matrix operations that are just mostly used for computer graphics. So if you notice for this is just the Mat4, it has a lot of matrices pre-calculated for defining a camera, like a perspective camera or isometric camera or whatever you want to look at. And all of these ones are just already included in the library. So if either you can add this library separately, or you can access this Abubu part that you see that I did here for defining the matrices.
Okay.
So when I
Is that
yes.
Is that parts of this went sort of past me, but the whole using the fourth dimensional representation to do rotations and stuff in 3D, is that because I know that like there's a whole construction to use quaternions to do that. Is that basically
Yes.
what's happening here?
Yes.
Okay.
Exactly. I think I forgot to add Abubu here. That's why it got sad.
Okay, so I guess I'm also sort of confused that you're doing all these different. I mean, I can sort of see doing one of these transformations in order because you're always changing your viewpoint.
Mm-hmm.
But then this other thing where you're first forming the object and then you're moving it in place, and you're doing that and rotating it. I mean, I would have thought that you would form it in place, like in the cube, since that's where the simulation is occurring. Missing something?
Form what in the cube?
Well, I guess the drawings you were showing it seemed like you were drawing, objects, which to me would be, for example, representative of where the action potential is, the wave, like with the space occupied by the action potential,
Mm-hmm.
and then you're translating it and rotating it so that it appears wherever it actually appears in the simulation cube, and then you're doing projection onto the screen. I would have thought that the first translation and rotation wouldn't be necessary because the action potential is already sitting there inside the cube.
So they are sitting inside the cube, but our coordinate system is between 0 and 1 because our texture functions work with 0 and 1s.
Oh, okay.
The clip space is between -1 and 1 coordinate system.
Oh,
So
okay.
if I place everything in that corner, if I wanted to do then any sort of rotation around it, you see if the center of that, it would rotate in a weird shape, like so.
Right. Okay.
The best thing is to just move it in there, and you can scale it to whatever value you want with respect to that center, and then you can rotate it around so it will stay in the center.
Okay. Cool. All right. Okay. So I guess the other thing I'm not too clear on, which I can figure out myself, is how all your sources how they're all organized.
So one thing is that there are two methods of looking at. If you have PHP installed on your computer, you can use this makefile to generate one single file, and it will generate it for you, or you can directly start opening the single file that is generated right now from my source codes. You see that it generates one single HTML that we were doing from the very first sessions. You see the init shader is there with the ID init, and then March shader that is doing the calculation for the fits on Agumo, and then I have added this volume rate casting shaders. PRC coordinate shader is here. The source code is placed there, so you can directly start working with this single file that is just doing everything. If you manage to debug it and find out what is the source of the error, you can pass me the last version, and then I will be able to modify it. But if you look at it, this is just very similar to those single file versions that we were doing from session 1 maybe to session 7 or 8. For all of them, I have added the multi-file version and a makefile that generated the final product. So generated the last one right now. Make. If I add it, so we worked with the cheat sheet in this session because I hadn't finished everything at that time yet.
Okay. All right. I'll try to figure some of this stuff out. I guess I'm like the relationship between make and PHP, and that connection I'm not familiar with.
So the only thing, if you create the make, if you look at the make file, I've explained it I think a couple of times right now. So basically the PHP command runs on the index.php, and basically it's a server-side solution to create the HTML page that is going to be displayed on the screen. So on this side, when I'm reloading the page, each time that I'm reloading the page, basically the HTML file is being generated by the server automatically. So a single HTML file is generated. And the PHP file, if you look at it, is very simple, similar to the HTML page, except you can have these PHP commands. And then the PHP commands that I have are these shader commands that I've included the shader.php, and that shader file is actually what is loading our source codes for the shaders. I see I've added a bunch of other lines for those of you who are interested. I've added different file types here as well. So if it ends with a .frag, it will generate this section as XShader fragment, so that in the final product you would see it as a fragment shader. It doesn't matter, these are for us only to read it. The moment that the browser sees that something is other than a script, it will disregard the source code. It will just treat it as a text carrying section. This is why we want to be able to read the source code from here so that we can compile it within the library. So it just changes fragment shader, vertex shader, or if it is ending with GLSL, it just treats it as shader. It just writes it as shader. It doesn't matter. You can just pass it to whatever you want. But some editors, they treat fragment shaders and vertex shaders differently, and GLSL files differently, so it's a matter of preference. In order to have code highlighting, instead of directly writing into a single file, I have written the shader files separately. So if you look at here, you have a bunch of shader files. So each file, init.frag, is, see, this is the content of init.frag, and if you look at the page when it gets loaded, it's loaded into this section, so the content of that file is loaded to that section.
Okay, cool.
Okay, So instead of having that, you just place those ones there, and it just makes it like a boilerplate that you can import all of these ones. If you don't want to set up a PHP server, you just can install PHP on your machine, and all you have to do is run the makefile, and it will generate the single HTML file that you can open as a standalone version.
Right, I have a Mac also, so I think that I've got PHP already on, you know.
So if you have PHP, you can already just type in make in the browser in the terminal, and then it will generate the single HTML file version of it for you.
Okay.
I
All right,
haven't
I'll try to work on
fixed the dependencies in the make file, so if you want to make sure that it's generating everything, you have to do a make clean first. But I will fix the dependencies as well. You have to add this vertex shaders and fragment shaders to the dependencies final file. Want to use the PHP. But the good thing is that when you do it like that, each of these codes that you open, the editor can immediately distinguish what they are. So like, you can open this, and the editor immediately understands that this is GLSL language, and it highlights the code properly for you. Whereas if you are working with the single HTML file, I know that people have been complaining about this. If you open the single HTML file, everything is just treated as JavaScript, and clearly these are not JavaScript codes. They are in a different language, so they don't get highlighted properly.
Right.
All of the functions are not being picked up. The only things that are picked up are these return statements or INT, which are generalized keywords. But it's very difficult to work like that. And I have the preference to work with the multi-file just because of the code highlighting, syntax highlighting.
Okay. Yeah, I've been using Xcode. I don't have MacVim on my machine yet, so I guess I have to go.
I can use any editor, basically. It's just all of these are basically in the end text.
Yeah, I mean, yeah, like I guess none of them completely highlights everything. Like, for example, even MacVim is not highlighting your HTML file properly, right? Or it's not choosing the right colors.
And if you just open the HTML, no, it won't be able to distinguish the section. It will treat it as HTML. And if you open an HTML file with MacVim, the only portions that are highlighted are the HTML and the JavaScript section. Like if you notice the JavaScript portion of the code is properly highlighted, it picks up new statements, location, function, var. These are JavaScript stuff that it can properly be picked up, but nothing beyond that. So it won't be able to recognize the GLSL. But if you open it as a GLSL file or .frag or .vert file, it will recognize it immediately.
Yeah, if you want to be lazy, Niels, that's what I've been doing. Is I'm sure Xcode has something similar that I use Sublime, and there's like a key shortcut for changing your syntax highlighting. So I'll have like the one file open, and then whichever part I'm looking at, I'll just change the syntax highlighting to JavaScript or HTML or GLSL.
Cool.
Not a pretty solution, but it works.
I wonder if it works in Xcode. Do you think it works in Xcode?
Maybe. I mean, I assume Xcode has some way to quickly change what syntax highlighting you're using.
I know that even here in MacVim, I'm able to change the syntax of the code that I'm looking at. Syntax highlighting. If I go to syntax, I can go to manual, I think. Go file types in menu, and then I can change. If you look at GL, it must be GLSL somewhere. It GNU defrag.
I can go to in Xcode. I can go to syntax coloring, and there's like a whole really long list of stuff.
Yeah, so you can change it. Yeah. Probably you can change it here too, but I have to check.
Trouble is, there don't seem to be shortcut keystrokes for them. Like, I mean, unless maybe I can figure out some way to establish them.
Yeah, you can configure it. Most probably, most of the editors allow it to do that.
Okay.
Anyway, So the last code that we worked with is, if you want to know the single file version, is fhn.html in that file, that folder PHP.
Okay.
Cheat sheet. Yeah.
Okay, so the cheat sheet's updated for the one for today. It's operational?
Yes.
Okay.
Let me copy it to the top as well. Levels up. Okay.
Yep. So I guess a lot of my command line computing skills are all outdated. And I don't think I'm not that I had Git around when I was programming at this level. Some probably try to learn Git at the same time.
Probably. I'm loving this Z shell that they recently introduced. It's not very recent, but I've recently come to love it because it also highlights your commands, and it also have completion, like for Git commands I can complete as well. So
Okay.
that's really nice.
Yeah, I mean, I guess what have I operated under? SH, CSH, Bash. I'm not sure if I've done ZSH.
Yeah, I think ZSH is one of the ones that right now really allows you to work a lot. It has very good binding with Git. For example, it shows that I'm on the branch master. When I was in Abubu, you see I'm on the development branch of the library. I don't mistakenly change something. It also shows you that if you make any changes, it shows whether those changes have been committed or added or not. So it's really useful.
Cool. So
for example, for this one, you see that there needs to be a git push. Here it shows that the changes have been added. It says that I have changes that are not added in this section. That's really good.
it looks like I've got ZSH. I guess ZSH comes with Macs also, right? I can type ZSH on the command line, and I get a percent prompt, which just suggests I'm in shell, but then it doesn't have anything fancy in it because it's just a percent prompt.
You can actually customize it. So this has undergone a heavy level of customization. It allows a lot of customization. I think it's Z, I think, is the package that I'm using to Britify Z.
Okay. All right.
I think I can stop recording here.